Okay, we're going to start a unit on complex numbers, but at the very beginning here, you're not even going to see any complex numbers because we're still going to be dealing with polar coordinates and using our trig knowledge, because what we need to do first is learn to convert between polar coordinates and Cartesian coordinates. We need to be able to go both directions, okay? So if I give you a pair of polar coordinates, like 2 pi over 6, you ought to be able to give me the Cartesian coordinates that would represent the same point in the plane. Or similarly, if we have some Cartesian coordinates, like 3, -3, you ought to be able to tell me what are the polar coordinates that give me this same point in the plane. All right, so let's take a look at an example. We're going to start with doing Cartesian to polar. Okay, so we're going to take Cartesian coordinates and we're going to convert them to polar coordinates. Okay, so I'm going to do 4 examples, I think, here. And so the first one is I'm going to take the Cartesian coordinates 5, 5. Cartesian, means that you're dealing with x and y, right? This is in the xy plane, so all of your coordinates are x, y. That's what Cartesian means. It's the kind of coordinates you've been dealing with since pre-algebra. So we got our regular old point here, 5, 5, and I want to know what are the polar coordinates for that point. All right, so I'm going to draw a little sketch of this situation. Let's see. This point is 5 units to the right and 5 units up. So it's about right there. So this distance is 5. And this vertical distance is also 5, right? So those are the Cartesian coordinates. You always have an x that tells you how far to go left or right, and a y that tells you how far to go up or down. Right? So now what I want are the polar coordinates. Well, the polar coordinates are this distance here that we usually designate as r, and this angle here that we usually designate as theta. Right? So what we're going to try to do is figure out what are r and theta in this triangle. Now, you may remember the work that we have done in the past where you're given a triangle. This is a right triangle, by the way. And, you're given some sides or some sides and an angle, and you're trying to figure out the missing pieces. And you can use all of that knowledge, but all the problems we're going to do in these conversion problems here are all going to rely on the special triangles, okay? So what I want to do is look at this and figure out which of the special triangles is it. Well, since the 2 legs are equal, that means these 2 angles are equal, and if those 2 angles are equal, they must both be 45 degrees or pi over 4, right? So this is really just a 45, 45, 90 triangle, which is, we usually label that 1, 1, root 2. Now let's just multiply all the sides by 5. So if we multiply this side by 5 and this side by 5, we got to multiply this side by 5. Okay? So that means that this radius is 5 root 2. All right, so what are the coordinates of this point in polar coordinates? Well, the distance from the origin is 5 root 2, and the angle that it lies on, it's on the terminal side of pi over 4. So those are our polar coordinates for the point 5, 5. All right, so this point and this point are the same point. We are just taking different routes to get there. All right, let's try another one. Let's try the point -1/2, negative root 3 over 2. Okay, these are my Cartesian coordinates. And again, I'm going to draw a picture. So in this case, I'm going to go 1/2 to the left, and then I'm going to go down root 3 over 2. That, of course, is at a right angle. So those are my Cartesian coordinates to get to this point down here. Here's the point that I'm interested in. And what I want to figure out is how far is that point from the origin. That's the radius. And I need to know what this angle is, right? I need to know what the big angle is. To figure out what this big angle is, it would sure help to know what this reference angle is right here. Okay, so as I said before, we're going to rely on our knowledge of the special right triangles here. So which one does this remind you of? Which of your special right triangles has a root 3 in it? Well, that is the 30, 60, 90, right? Or the pi over 6, pi over 3, pi over 2 triangle. And usually we have those side lengths labeled like this, don't we? Right? We have a hypotenuse of 2 and a leg of 1 and a leg of root 3. But the root 3 here is divided by 2, and the 1 is divided by 2. So I guess we need to divide everything by 2, don't we? So we're just going to rescale this triangle. We're going to divide this by 2, divide this side by 2, and divide this side by 2. So that means the hypotenuse is 1, and the legs are 1/2, and root 3 over 2. So this is still a 30, 60, 90. It's just half as big as the one that we're using a lot of the time. Okay, so this angle right here, this reference angle, it comes across from the root 3 over 2. What comes opposite from the root 3 over 2 in this picture? Well, opposite from the root 3 over 2 is this angle pi over 3. So this reference angle here must be pi over 3. And then how long is this hypotenuse? Well, over here, the hypotenuse is this side, and it's 1 unit. So that point is 1 unit away from the origin. And we still need the actual theta, right? Because the actual theta is measured from the positive x-axis. So if I go over to here, that's a straight angle, which is pi, or 3 pi over 3, and then I add another pi over 3, so this must be 4 pi over 3. All right, so this point down here is, it has these Cartesian coordinates, but it also could be described with the polar coordinates 1, 4 pi over 3. All right, so this pair of coordinates and this pair of coordinates describe exactly the same point down there in the third quadrant, but they just give you different ways of getting there, right? You can either go a half a unit to the left and half of root 3 units down, or you can follow the angle whose terminal side is 4 pi over 3 and go 1 unit out from the origin along that line. All right, so let's try one that doesn't really even involve a triangle. 0, 4. And I'm going to draw that. Let's see, that's 1, 2, 3, 4 units up, right? It's on the y-axis. We go 0 units to the right or the left, and then we go up 4. And so we need to know the polar coordinates for that. Well, how big of a rotation did we make to get there? Well, that lies on the terminal side of the angle that goes straight up there. So that's pi over 2, isn't it? And the radius, obviously, is this distance right here, because how far did you go from the center? You went 4 units from the center, and so the polar coordinates of that are 4 pi over 2. Right? That we went 4 units in the direction of the angle pi over 2, the terminal side of the angle pi over 2. Let's do one more that is on an axis. What if we have negative 5, 0? Okay, so where is negative 5, 0? Well, we go 5 units to the left, and then we don't go up or down at all. All right, so here's where negative 5, 0 is in the Cartesian plane. And now how do we get to that in polar terms? Well, what angle does it lie on? It lies on this angle that has its terminal side going straight out to the left. So that's pi, isn't it? Pi is the angle whose terminal side points straight out to the left. And how far is it from the origin? Well, it's obviously 5 units away from the origin, right? It's not negative 5 units away, it's just 5 units away. That can be a little bit confusing because we are so used to all of our values that go off to the left being negative, but we're not using this 5 to tell us what direction to go in. The pi tells us what direction to go in. So this point is at 5 pi. Okay, so a lot of people get a little confused because in Cartesian it was a negative 5 and in polar it's a positive 5. But that's because in the polar coordinates, the fact that you're going off to the left is indicated by the fact that you are going along the terminal side of the angle that measures pi radians. Okay. All right, let's have you try one. I've given you a pair of Cartesian coordinates here, 2, negative 2 root 3, and let's see if you can convert that to polar coordinates. So hit pause and give yourself a little time to see if you can do that before we look at it together. All right, so let's look at this together, see if you got it right. I'm going to make a diagram and plot this point. I'm going to go 2 units to the right, and I'm going to go 2 root 3 units down. Okay, and I need to know how far is this point that I've reached from the origin, and I need to know what is this angle. And of course, to figure out that angle, it would be very helpful to know this angle. Okay, so when I look at this triangle, I'm trying to think which special right triangle might this be. And I see the root 3 in there, so that immediately makes me think that I should probably be looking at a 30, 60, 90. So let's take a look at our standard 30, 60, 90, where the hypotenuse is 2. That leg is 1, and that leg is root 3. But in this triangle, the leg here is 2 root 3. So I need to double the root 3. So I need to double this hypotenuse, and I need to double this leg down here. In other words, I made all the side lengths 2 times bigger than what I use most of the time. So one of the legs is 2 root 3, we got that. One of the legs is 2, we got that. And then the hypotenuse is 4. Okay, so that's the distance of this point from the origin. It's 4 because that's the length of that hypotenuse. And which angle comes across from this 2 root 3? Well, the angle across from that is pi over 3. And if this reference angle here is pi over 3, then what's this big angle? Well, it's pi over 3 less than a whole rotation. A whole rotation is 2 pi, which is 6 pi over 3. And so since this is pi over 3 less than that, it must be 5 pi over 3. Okay? So the coordinates for this point are 4 and 5 pi over 3. So these are the polar coordinates for the point that has these Cartesian coordinates. All right, let's go the other way. Let's try to go from polar to Cartesian. So we're still trying to convert, but this time we're going to start with a polar example and convert it to Cartesian coordinates. So let's try this point here. This is a pair of polar coordinates, and I'm going to use pretty much the same technique here that I did when I was going the other way. I'm going to start out with a diagram, and the angle here is 3 pi over 4. So hopefully everybody kind of already knows in your head right where that is, right? 3 pi over 4 is pi over 4 less than a whole, less than a straight angle, right? So it comes right in the middle of the second quadrant. And how far do we go from the origin? We go 1 unit from the origin. All right. Well, what do I need to know to get the Cartesian coordinates? Well, I need to know these distances, right? I need to know how far am I to the left of the origin, and then how far up am I from the x-axis. I need to know these two values. That's the x, and this is the y. Okay, so again, we need to think about our special right triangles here. If this angle's pi over 4, clearly we're looking at a 45, 45, 90. And what's our usual 45, 45, 90 look like? We usually have 1, 1, root 2. Okay, but on this one, the hypotenuse is only 1. So I'm going to need to make this hypotenuse 1. So to do that, I'll divide this length by root 2. And if I divide this length by root 2, I need to divide both of the other lengths by root 2. Okay, so here is a 45, 45, 90. And if the hypotenuse is 1, then both of the legs are 1 over root 2. Now this 1 over root 2, of course, has to be negative because it's an x-coordinates going off to the left. This one is positive, though, because we're going up. Okay, so this point here, whose polar coordinates are 1, 3 pi over 4, has Cartesian coordinates 1 over root 2, 1 over root 2. Or, if you are fastidious about not having roots in the denominator, you can write root 2 over 2, root 2 over 2. That's entirely up to you. All right, so going from polar to Cartesian, we're using much the same technique, right? We draw a diagram, we get a triangle to work with, and we figure out in this case, the two missing legs. That's what we're always going to be missing when we're going to Cartesian. Let's try another one. Let's try one with a negative radius. How about negative 1, 3 pi over 4? All right, so remember, what does a negative radius mean? Okay, the angle here is 3 pi over 4, so that's going off this way, right, just like in the first example. But the negative radius means that instead of going out in the 3 pi over 4 direction, we go off in the opposite direction, right? So we're going to go 1 unit in the opposite direction from 3 pi over 4. And what angle is that? What angle is opposite from 3 pi over 4? Well, this angle right here in the middle of the 4th quadrant, of course, is going to be 7 pi over 4, isn't it? It's going to have a pi over 4 reference angle. And so what are the Cartesian coordinates for this point? Well, we need to know how far do we go to the right and how far do we go down to get to it. And you'll realize this, of course, is the same triangle we had in the last example, right? The legs are both going to be 1 over root 2. But this leg will be negative because, of course, it's going down. It's a negative y coordinate. All right, so the Cartesian coordinates here are 1 over root 2, negative 1 over root 2. All right, let's try one more that relies on a triangle, and then we'll look at some points that lie on the axes. All right, so let's take the point negative 2 pi over 3. Okay, so we got a radius of 5, and our angle is negative 2 pi over 3. How do you get to negative 2 pi over 3? Well, first of all, since it's negative, it's going to be a clockwise rotation, right? And remember, a straight angle it would be going around to negative pi. But negative pi is the same as negative 3 pi over 3. So negative 2 pi over 3 is going to be pi over 3 less than that, right? So here's negative 2 pi over 3. All right? Feels like the same stuff we've been doing forever, right? And so here's the point we're interested in. We're interested in this point right here. We want its Cartesian coordinates, okay? And it is, didn't label the distance there. It is 5 units from the origin. Right, so the coordinates that we want for the Cartesian system is going to be this x distance and this y distance. Right? And so we need to figure out what are the side lengths there if this angle's pi over 3. Well, again, I'm going to, obviously, I know what triangle I'm working with because the reference angle there makes that clear. So usually I've got, put the right root there. Usually I've got these lengths on my 30, 60, 90, but now I want the hypotenuse to be 5. Okay, so I need to multiply 2 by something that will make it 5. Well, to make that 5, I need to multiply by 2, I need to multiply by 5 over 2, right? Because if I multiply by 5 over 2, then the 2's cancel out and leave me with 5. So if I multiply this side length by 5 over 2, I need to multiply all the other side lengths by 5 over 2. So this leg down here becomes 5 halves, and this distance here, this leg is 5 root 3 over 2. Okay, so I took my regular 30, 60, 90, multiplied all the side lengths by 5 halves. I figured I needed to do that because I needed a hypotenuse that was 5 units long. Okay, now which leg is opposite from that pi over 3? Well, here's the pi over 3, and here's the leg that's opposite from it. So this distance here is 5 root 3 over 2, because it's the leg opposite from the pi over 3. And of course, this y-coordinate is negative, right, because we're going down. And then the other leg, the one that's adjacent to the pi over 3, is just 5 halves. And it also has to be negative, right, because we're going off to the left. Right, so the Cartesian coordinates for this point are -5/2, -5√3 over 2. Right, so here are my polar coordinates. And now I've got the Cartesian coordinates. Okay. Let's look at an example where we're not going to have a triangle. How about the point 3, 0? And I'm going to write polar here because if you just look at that and I don't tell you it's polar coordinates, you might just assume that that's Cartesian coordinates, right? You can't tell the difference because nothing here has a pi in it, so it doesn't jump out at you as being an angle. So where is that? In polar coordinates, the angle is 0, so that's the angle whose terminal side goes off to the right. And I'm going to go 3 units out in that direction. So there's where the point is in polar coordinates. I went 3 units in the direction of the angle 0. And what are the Cartesian coordinates here? Well, I don't need to mess with triangles or anything. I can just look at the picture and tell. I went 3 to the right and I didn't go any up or down. So just sort of as an oddity or a coincidence here, the polar coordinates and the Cartesian coordinates look exactly the same there. All right. By the way, notice the polar coordinates could have been expressed as 3, 2 pi. And in that case, the polar and the Cartesian don't look exactly the same. All right, because 2 pi and 0 are coterminal. All right, let's try another one of those. How about 3 pi over 2? All right, so let's draw the picture. Which way is pi over 2? That's the angle that goes straight up, right? And we're going to go up 3 units. So if we go 3 units from the origin in the pi over 2 direction, again, we don't need to mess with triangles or anything because we can just look at that and tell what the Cartesian coordinates are. So we didn't go any to the left or the right, and we went up 3. Okay. So actually the ones that are on the axes are pretty easy in the sense that you don't need to worry about a triangle, right? How about you do 3 pi? Take a moment, hit pause, and see if you can convert 3 pi, those are polar coordinates, into Cartesian coordinates. All right, so let's see. What's the pi direction? Well, the terminal side of pi goes straight out to the left, and we're going to go 3 units in that direction. And so, again, once we get the point located, we don't really need to do anything. We just look at it to say what the coordinates are, right? The Cartesian coordinates. How far do I go left or right? Well, I go 3 units to the left. So that means the x-coordinate is -3. And I don't go up or down any at all. So the y-coordinate is 0. All right. So, just a couple of comments here. First of all, notice that the special right triangles, as I keep saying over and over, they just won't go away, right? We keep using them over and over. And so that's going to continue for a while. And my other comment is, I said at the beginning we were starting to deal with complex numbers, and you didn't see any complex numbers in this lesson. So if you'll hang on till the next lesson, I will show you how all of this stuff has something to do with complex numbers, And just to give you a little bit of insight into where we're headed here, it's going to give us the ability to do some things with complex numbers that you couldn't do with the way you treated complex numbers in Algebra 2. For example, we're going to be able to come up with things like, what is the cube root of I? Okay, and we're also going to be able to raise complex numbers to powers. So for example, we're going to be able to take 1 minus I and raise it to the 11th power without ever having to do any FOIL. Okay, so those are some things that we're going to be able to do in this unit. We're just kind of building up the background knowledge to get us to where we can do that.